Hi guys. So this is Tyler Maley, your math professor, making a video for Kathy Almy's 3.2. So this lesson is looking a little further in correlation. So what I'm doing is last section we went through scatter plots, and now we're doing a little more with correlation. Just prepping you for something you're going to do in statistics called regression, which is has a lot of really great applications. All right, so if we take a look at the graph here, um, across the top, our title is "Many and Developing Nations Struggle to Afford Food." Right, so that just gives us kind of a snapshot of what the graph's about. So if we look further, we can see that our dependent variable right along the vertical axis, our y-axis, is the percent that cannot afford food in the past year, while along the x-axis or the horizontal axis, which is also called the independent variable, right, that we looked at last section, is the 2012 GDP per capita. Right, and you can look up what GDP means, but essentially it's a type of measurement we can think about as far as maybe trying to put like a wealth on a country. We can also see that we have a key. Right, so let me grab some ink here. Right, so here we have this key here. So the green squares are advanced countries, the orange circles are emerging markets, and the purple looking triangles are developing economies. Right. And we can also see that there's a source here, right? This is from pewresearch.org, so this is a pretty reliable research group that where we can get information from. Something else to note is that not every symbol is named right, but certain countries are named, so we can see like here's the U.S. right. All right, so let's now that we know about the graph, let's begin to look at the questions now. Right. So number 1A, write a sentence to summarize the trend shown in the graph. Right. So if we look at this for a little bit, a trend that you can see is essentially as we go to the right. Right. In other words, as we increase the country's GDP, notice the y values tend to go down, right? So essentially, we kind of have this maybe not quite a linear trend, but some kind of trend that maybe looks something like this, right? So it's kind of this decreasing trend, right? As my x value is increasing, my y values are tending to go down, right? So the richer the country is, there tends to be less people who can't afford food, right? So let me just erase this. Right, so that way we can see the graph still. So let me type a sentence here for you, right? Something that we could say. So we could say something like countries with higher GDPs have lower percents of citizens who cannot afford food. Right, so something like that. Oh, I misspelled percents. No, I don't think I did. It just doesn't like that, right? But that's fine. Right, that's the word. I don't know why word doesn't like that. All right. Well, it doesn't seem to like that. Right. So that's what we were describing, right? In words. So 1B, it says, does the United States follow the trend shown in the graph, or is the United States an exception? Explain your response, right? So if we look at the graph a little bit, we kind of follow this trend. It looks like the United States is not where it should be, right? Again, as we go, as we increase the x value, the y value seems to be decreasing. So if I had the same x value as the U.S., I would expect the U.S. to be somewhere down here, right, to follow the trend. But notice it's above, right? It's above even Australia, or it looks to be pretty, fairly in line with maybe Greece or South Korea. But notice they're way to the left. So this is maybe an exception, right? It seems to be too high, right? So that's what I would say there, right? So if we want to put this in words, we could say something like the United. Let me capitalize United. The United States appears to be an exception. Countries with GDPs as high as that of the United States usually have a much lower percent of citizens who cannot afford food, right? So maybe something like that might answer all the questions. So then part C says estimate the percent of citizens who cannot afford food in the past year in a country that has a GDP of 48,000. Right, so if we look back up here, if we were to pick someone with a GDP of 48,000, so let me, use my mouse here. I'll try to go ahead and just erase this and grab my ink back. Right, so 48,000 GDP might be somewhere here, right? So maybe this is 48,000. So maybe an X value I might predict might be somewhere around here. We have to try to estimate where this might be. So I don't know, maybe it's 10,000 if you want to, maybe somewhere between 8 and 10%, right? Somewhere around there. So we could just write that, right? Maybe 8 to 10%. Right? So that's pretty sloppy. Let me just fix that. There. Right? Good. Right, so that was just to get us thinking about scatter plots and some trends that can happen, right? So given some data, we can kind of look at some trends to kind of make sense of what the data looks like, what's going on with the data, and also it can help us, as we'll see, might be able to make some predictions or some educated guesses sort of with what might happen in the future, right? What trends are going on, right? And in statistics, you're going to learn some things maybe with extrapolation and interpolation to maybe some things to be cautious with doing some projections, but for right now we're not going to be worried about that in this section, right? So it can be really useful, but we have to think about some caution. So here's just some guiding questions that you can read over that this lesson is supposed to help try to address. So and I won't, necessarily like read over every part of this lesson with you. So this is like taken out of a book that we consider like a work text. So some of it might be kind of like a textbook feel, while other parts of it are more of a like a worksheet or a workbook, right? So if we look on the next page, this is kind of the textbook part, right? So so this is just talking about linear correlation, right? So it's just pointing out that if the data points tend to kind of follow this linear line type of fashion, then we have what's called linear correlation, and what we can do is find a line that we call the line of best fit, or the trend line, to kind of model the data. And if that line has a positive slope, then we call that a positive correlation, right? So if we're going left to right, the trend line's going up, so it's increasing, right? Where this other graph here is a negative linear correlation, right? So notice the slope of the line is going downward, and as the x values increase, the y values go down, right? So you can see what I mean. So as the x increases, notice the y coordinates are going down. Where over here, as x increases, the y coordinates are actually going up or increasing, right? So we have a positive correlation, right? So here we want to think about number 2. We're given a situation and trying to think about if we would expect a positive or negative correlation. Right. So 2a says the number of customers a company has and the total revenue for a company. Right. So I might just draw a line here. Right. So this is the number of customers. And the revenue, right, is along the side. So it's reasonable to think as my number of customers increase that I'm making more money, right? So, we might have a linear trend, something like this, right? So this would be a positive, right? So as x increases, my y increases. So 1b, right? So instead of number of customers, right, we have number of hours of overtime, right? So hours of overtime. Along the y-axis, we have the number of hours spent with family. Right? So if we think about this a moment, the more overtime I work, the less hours in the day that I have to be at home, right? The day's only 24 hours. So if I work 12 hours, I only have 12 hours to be home, right? So as the x value increases, right, as the hours of overtime increase, you would expect the hours with the family to decrease, right? So in other words, we would have a downward type of trend, right? So this point is less overtime than this point, right? But this leftmost point gives me more hours with my family, where this one I would have less, right? So this we would expect to be negative, right? So with these, you just got to kind of think about what kind of trend you would see. So part C is the cost of a car and the number of people willing to pay for it. So the way to think about this is, you got to assume you have just, one car, right? Maybe we have a, 2018, Silverado, right? So if you think about this for a moment, if I have just this one truck, right, then if I want to sell that truck for $10,000, let's say, right, versus maybe selling it for $1 million, right? How many do you think more people would be willing to pay $10,000 for this truck or $1 million, right? So the same truck, right? So more people are going to be able to afford this, and more people would be willing to pay $10,000, right? Where very few would be willing to pay $1 million, right? So if you kind of use that as your thought process, right? So the x-axis would be the cost of the car, and the y-axis is the number of people willing to pay. Then as the cost goes up, we would have less people, right? So that means we're going to have a downward trend, right? So we're going to have, if here's maybe the 10,000 and here's maybe the million, right? We would have more people, right, willing to pay the 10,000 versus less people willing to pay the million, right? So this has a negative slope, right? A negative linear trend, right? Negative correlation. So part D talks about the number of hours a student spends at an ACT prep course and her ACT score. Right, so with this one, along the x-axis, we have the hours, spent prepping, and along the y-axis, we actually have ACT scores. Right? So if you spend more hours, you would assume that your score would go up, right? So as my hours increase, you would think my ACT score would tend to go up, right? So this would have what we would think would be a positive trend. Right? Right? So then you can see here that when two variables are linear correlated, the relationship between them can be described by a trend line, right? So that's some things we're going to explore next, right? So there's an example here that you can read over and puts this into context, right? So we have this data of arm span and height, and when we plot it on a trend line, you can see you get this graph, and this looks like it has a linear trend, right? It looks like the data, tends to have this type of trend, right? A linear trend. It's as x increases going up, so it's actually a positive linear correlation, right? So we're going to use in the statistics class. You're going to learn how to calculate these lines. You're going to use technology to do so. In this section, since we're just kind of prepping you for that, it'll be provided for you, right? So so here is the equation of the trend line, right? Y equals 0.9x plus 7.3. And if we want to use maybe different variables, so here they use an A for arm span and H for height, right? We can swap those out for X and Y to make them a little more meaningful, right? So there's your equation. And then this next graph here, right? We have the trend line plotted over top of the scatter plot, right? So you can see how that works, right? So this line up here, I just kind of eyeballed, right? Just trying to draw, but you can use technology to actually find the best fit line, and you have to do what we're going to look at are residuals and trying to basically make the line be closest to most of the all the data points, right, as close as possible. So we're gonna see what that means a little bit, right? So just prepping you for those statistic ideas that you'll be seeing in the coming weeks, right? And then actually here in this example, they're plugging 67 inches arm span and trying to estimate the height of that person, and so we can use that trend line to kind of make that prediction, right? So our line is guessing that if someone has a 67-inch arm span, they'll be 67.6 inches tall, right? And that's actually a true observation of the human body, right? Typically your arm span is approximately equal to your height, right? It's going to be very, very close. Right, so you could try that out if you want. Right. So then this next example is one for us to work through, and this is interesting. It's not exactly given to us in a linear format, right? At least not this graph, but it's earnings and unemployment rates by educational attainment, right? And this is actually a really, really cool graph and useful graph. It's published by the Bureau of Labor Statistics, which is a government agency that tracks statistics, for the good of the public, right? So it's good for someone to be looking out for, the unemployment rates and all those kind of things. Right. And I used to, before I was hired as full-time math professor, I worked in admissions before, and I used to use this type of chart a lot. So I used data when I would work in admissions or give presentations, because I'm a mathematician, but I enjoyed doing that. But this graph's really cool. So you'll notice it's a double bar graph, right? So we have bars on the left and bars on the right. The bars on the left are unemployment rates, and the bars on the right are median weekly earnings, right? And remember, median is right in the middle, right? So 50% higher, 50% less, right? So then we have broken out by educational groupings down the center, right? So we have less than a high school diploma, all the way up through a doctoral degree, and so forth, right? So part A asks us to describe the general trend you see in the graph. Are there exceptions to the general trend? Give examples if possible. Right. So the general trend that we see, right, is the higher the education, right? So as I go up on the education tiers here, notice that my weekly earnings tend to go up, right? So these tend to go up, my median earnings. And notice my unemployment rate actually goes down, right? So over here, right, notice we had 9% for less than high school diploma, and it just keeps going down all the way up to 2.1 for the doctoral degree, right? And I want to describe maybe what's going on here, right? So you might be seeing that a doctoral degree is above this professional degree, but the doctoral degree seems maybe a little worse, right? The median earnings are a little less than the professional degree, and professional degree has a little less unemployment rate. So just to kind of, so that makes sense. A professional degree is like, getting like a doctor of medicine, so you're, a medical doctor, or getting a law degree and so forth, right? So that's considered a professional degree. A doctoral degree is more for academics, right? So like if you get, a doctor of philosophy in mathematics, or a doctor of philosophy in, English or so forth. So this is more for academia, where a professional degree is a doctorate degree, but really meant for the workforce, like a doctor of pharmacy, for example, right? Is another type of professional degree. So professional degrees tend to make more than a doctoral degree. Right, a lot of doctorates, are employed by public colleges, universities, and maybe not making as much as you could if went in the private sector. Right. Right. So we looked at describing the trends that's seeing, and then the second question is, are there any exceptions to the general trend? And of course there are exceptions. And basically what that's saying is, just because you have an associate's degree versus someone who has a master's, does that mean that the associate's degree person will always earn less than the master's degree, for example? And that's not necessarily true, right? You could have someone with maybe a master's in education, let's say maybe making, 50 grand, right? But then you could have someone with an associate's degree in maybe nursing, and they're making, 70 grand. Right, so that's quite possible. So it depends on the field, right? Is really the exception. So this it isn't by any means the end all, right? So that's what we could say for part A, right? So we talked about the trend and gave some examples and some exceptions that could occur. All right. So part B says, notice that under the last bar on each side of the graph is an average. These numbers are not the simple means of the values listed for each category, unemployment and median weekly earnings. How do you think they were calculated, right? So for part B, basically what they're saying is if you average all these numbers on the bars, right? So if we take 1,591 plus 1,639 plus, add all these up and then divide by how many there are. So 1, 2, 3, 4, 5, 6, 7, 8. You will not get 839, right? And the reason being is there are a different number of people in each category. So these would actually be this would actually be a weighted average, right? So this would be a weighted average, right? So like a grade point average, GPA is an example of a weighted average, right? So, right, we looked at weighted averages, I think it was last week or 2 weeks ago, right? So for part B, we would just say that so each average listed is a weighted average whose weights are the number of people in each category, right? So since there's a different number in each category, that's why we need a weighted average. Right? And then here, we're asked to fill in this table. So it says to analyze the data's relationship further, convert the earnings from weekly earnings, assuming all to hourly earnings, assuming 40 hours per week, and then record the unemployment rates and the hourly earnings in the table provided. Right. So for the first one, like if we look at the doctoral degree, they make 1,591. Right. So if I open up my calculator, right. So what they're saying is if I take 1,591 and divide it by 40 hours, right, we can get the hourly rate, which is 39.775, right? So for the hourly rate, you're just going to take each of these and divide by 40. So to speed this up, I'm just going to fill the table in for you, right? I assume you can divide by 40, okay? And then the unemployment rate, you're just pulling from that table as well, right? So the unemployment rate was 2.1, 1.9, 2.8, and then 3.5, 4.5, 6.0, 6.0, and 9.0. Right, so we're getting those values. Then the hourly earnings, like I said, I'm just going to go ahead and calculate those, and I'm just going to round to the nearest cent every time. So we'd have 39.78 for the first one, 40.98, 33.15, 27.53, 19.8, 18.53, 16.70, and 12.20. Right. So in part D, we're just filling in, plotting these points on a scatter plot, right? So we have the unemployment rates are x-axis and hourly earnings is the y, right? So let me just plot these really quick, right? So we have 2.1 and 39.78, right? So maybe somewhere around here. Oops. And then 1.9, 40, maybe like here. Oops. And then 2.8. Right. Right, so I'm just going to pause this and finish plotting these and then catch back up with you. All right, so I got all these points plotted, right? So you can see we kind of have this linear trend going on, right? So again, if I were just to kind of eyeball this, we might see maybe a trend line looking something like this, right, in this direction. Right, so if we keep going on, part E says, what does your scatter plot suggest about the relationship between the earnings and unemployment rates? What kind of correlation is suggested? Right, so what we could say here is the scatter plot shows that the unemployment rate tends to be lower if the earnings are higher. The correlation is negative. Right then. Right, so we might say something like that. right? So the unemployment rates tend to be lower if the earnings are higher, right? So like these points, right? The higher points are with the lower unemployment rate. So then here we're given a line of best fit, right? That was calculated by technology, and we want to graph this line then, right? And so to do so, we want to pick 3 points to graph this line. So we're just going to plug in 2 for u and see what h is, right? So h would equal negative 4.2 times 2 plus 44.9. Right, so this is when u is 2. What's h? We're trying to figure that out. Right, so if you plug this in, you should get 36.5. Right? So we would do the same thing for 4 and 6, right? So I already calculated these here. So this should be 36.5. The next one should be 28.1. And then if you plug 6 into this, right, and for you should get 19.7. Right? So don't forget order of operations, right? We would multiply before we add, right? So this would be equal to what? Negative 8.4 plus 44.9, and then now I can add these together, right, to get the 36.5. Right? So now if I plot these points, so 2, 36.5, maybe it's here. And then 4, 28.1, might be roughly here. And then 6, which is 19.7, which might be here. Right, so these 3 dots, if I connect them, is what we're estimating the trend line to be, right? And that isn't the best line here, right? But hopefully you get the idea, right? So that's what we're estimating the trend line to be. So then part G is that we want to predict the hourly earnings for a job level that has an unemployment rate of 5%, or U equal to 5. So let me just write down the equation here, right? So H is equal to negative 4.2 times U plus 44.9. So in this case, we want to plug in. Wait, no, that was a U. Right. So in this case, we want to plug in U equals 5 and solve for H, right? So H would equal negative 4.2 times 5 plus 44.9. Right? If we want, just plug this in our calculator. So let me clear here. So we want to do negative 4.2. Right, so negative 4.2 times 5. And then we want to add 44.9. And we get 23.9. Right? Whoops. Oops, what was 23.9, I believe. Yeah, it looks like 23.9. Right, so H equals 23.9. Right, so we would expect someone maybe with a 5% unemployment rate, maybe to make around $23.90 an hour. Right. So next thing we want to talk about is a residual. So a residual is the difference between an actual and an observed value, right? So let's talk about observed versus predicted, right? So if we go back up to my equation, right, then if I consider, let me just pick a different color here. Right, if I consider this value, and I'm just going to go straight up and look at a value that's on the line, right? So if I go straight up, these 2 points have the same x value, right? So this x value for this point was, what, 4.5, right? So this point has an x value of 4.5, and this point also has an x value of 4.5, right? I know the y coordinate of this x value, right, which was 19.8, right? And I'm just getting that up here from my table, right? And if I want to know the y value that's on the line, I could simply just plug that in, right? So my equation is h equals, what, negative 4.2 u, I'm plugging in 4.5, and then we would add 44.9. Right, so if I just plug this in, so 4.2, negative 4.2 times 4.5, and then plus 44.9, we get y value of 26. Right? So since they have the same x value, this guy and this guy have a special name, right? So we want to talk about observed versus predicted. So if you think about it for a moment, it makes sense that this one is called the observed value, right? This data point represents a value that actually existed, right? Therefore, we observed it, right? Where the line we're going to use to make predicted values, right? So this is the predicted value, right? So what we're looking at is the difference in the y values, and that's what we call the residual, right? The distance between the observed value and the predicted value. So the whole idea with a line of best fit is to have the least distance in between all the points and the line, right? And it's not just any distance; it's we're going straight up, right? We want points with the same x values, right? So when I think distances, I'm thinking about these. Right? So like from here up to the line. Right? So so this distance is the residual. Right? So the residual is the observed minus the predicted. Right? So if I have a negative residual, it means that the observed value is less than the predicted, right? So like this case would be a negative residual, right? So this guy would have a negative residual, right? It literally just means my data point is below the line for that x value, where this guy here would have a positive or nearly zero residual, right? Because it's really close to the line, or it's above, right? So very positive. It's a positive, but a very small number. Right? So if we go back here, that's what this talks about, right? So I kind of try to give you a visualization of what a residual is, which will help you with stats, right? All right, so here we have this table, and we're trying to figure out should this professor give a final exam, right? So it's having us think about you know, is the final exam grade necessary to give, right? So what we want to look at is, does a student's overall grade before giving the final exam, is that, you know, a good predictor of the student's actual final exam grade, or should we still give a final exam, right? That's what it's asking. So you can see here we have a line of best fit provided, right? Final exam grade equals this value down here, right? So what we want to do is fill in this table, and then have some follow-up questions to go along with that, right? So to make this go a little quicker, I made the table in Excel here. So let me just fill this in, right? So we can use Excel to calculate this. So the predicted final exam score, right? So in Excel, I want to start this with equals, right, for an equation. And we want to take 1.0138, right? I'm just grabbing that line of best fit equation on the bottom of that table. And we want to multiply it times the overall grade, right, which would be this number, right, this cell. And then I want to subtract off 4.1629, right? And that will calculate the residual here. Right, and I can just fill this down, or not the residual, excuse me, the predicted final exam score. Right, it's calculating the y values essentially. Right? So all of these values are predicted, where these values are observed, right, in the column B. Right, these are what actually happened. This is what's predicted. So then, if I want to calculate the residual, right, I'm going to take my observed minus my predicted. So I want to take this guy minus this cell, right? And I can just fill this down, and it'll do it all the way, right? So like if I double click here, you can visually see that I'm taking this number minus this number, right? So it's doing that all the way down, right? And if you wanted, we could round these to maybe just one decimal spot, right? So I'm just going to highlight these, and there's a button up here to decrease your decimals. So we could, maybe just round to one decimal spot if you wanted. Right, just makes it a little easier and cleaner to talk about. Right, so part A is just doing, parts A and B are just doing that, right? So using the linear trend line and rounding to the nearest tenth, it even says. And then part B is that we're going to find the residuals, right? So you could do this by hand, or we have this done in Excel. So I'm just going to take a screenshot of this table and throw it into OneNote, right? Right, so I have that here as well. So part C says, what does a positive residual tell you about the student's performance on the final exam? Right, so if we look at just the positive scores, what you can see is that the observed value is bigger than the predicted value, right? So in other words, all the positive residuals mean that the student actually scored higher on the final exam than we predicted using their grade before the final exam grade, right? So for part C, how we could maybe put this in words, maybe as simply as we can, we could say the student performed better than expected, right? So for example, if we look at like this student, so maybe like this student here, right? This 66 is their grade before taking the final exam. Using our model, we predicted that they would get a 62.7 grade on the final exam, but actually they got an 82%, right? So this positive residual means that the student did better than expected, right? They got a much higher grade on the final than we expected based on their grade before the final, right? So then part D says, what does a negative residual tell you about the student's performance on the final exam, right? So they would be similar, but just the opposite, right? So it would tell us that the student performed worse than expected, right? For this, like putting it in context. And then part E says, how well do you think this model given by the equation of the trend line predicts the final exam score? Does the professor still need to give a final exam? Why or why not? So you could make some argument here, right? But thinking about this a little bit, We do have cases where, the residual is nearly, one whole letter grade or more, right? So like these students I'm highlighting in green, right? Those are nearly, 10 percentage points, or the lowest one here is nearly 2 letter grades, right? So I would say that there's, data to suggest that we should still give the final exam, because we still have these students that maybe didn't try hard in the term, or maybe something finally clicked and suddenly they're doing much better on the final exam, right? So so that's something I might say. So if we wanted to put this, let me type this up, we could say something like, some of the final exam scores are much higher or lower than the equation predicts. A final exam is probably needed, right? Something like that, right? So some students are doing much better or much lower than we would expect, right? So like this student here who has a 70 before going into the final, we would expect them to get around a 66.8 on the final exam, except they actually got a 52, right? So this is a negative residual. So they actually, were almost about a grade and a half less than what our motto would predict, right? All right, so that's all I have for this video. Let me know if you have any questions. Thanks.